When we use real numbers in computer software, behind the scenes we use a binary floating point representation. Now in a previous video we've already looked at generic floating point representations as well as the specific IEEE 754 floating point standard, which is used by most of our processors and our floating point implementations in our different languages. Now, in this video, what we're going to do is look at examples of taking bit patterns in a generic floating point representation and determining what they mean in human decimal form. So we'll convert from the binary to scientific notation and eventually to some signed fractional representation of the original value. We'll also look at some examples where we take real valued decimal numbers and figure out how to convert them into our same floating point representation. And we're going to do this with 8 bits rather than the IEEE standard, just because we don't want to slug through 32 or 64 bits on paper, and an 8-bit representation is just as good as any. So let's get started by defining our representation in 8 bits. I'm going to keep the sign bit up here at the top, just 1 bit needed for that. And when I do my own floating point, I tend to like my significant bits to be next, but it is really of little consequence at all, the order of these 3 parts. And so in the lower order bits, I will put the exponent. We need to pick how big our significand will be versus our exponent. And I want more bits of accuracy and precision here, so I'm going to go with 4 bits for the significand and the remaining 3 bits for the exponent. Now I went to random.org again to get 2 random 8-bit patterns, so 2 bytes in binary. And I wanted 1 positive number and 1 negative number, so I just am going to copy down the first 2 of those from my screen. And the first negative one is 0, 0, 1, 0, 0, 1, 0, 0. And then the first negative one is 1, 1, 0, 0, 1, 1, 1, 0. Ooh, nice. And so we're going to figure out what each of these 2 4-bit or 8-bit patterns means. But in each case, there's 4 different interpretations, because the significand could be normalized or denormalized, and the exponent could be biased or unbiased. So we have to deal with that for each of these. Again, the significand could be, say, denormalized. I'll just write denorm. Or it could be normalized. Norm. Same for this one. Denormal or norm. Now the exponents might be unbiased, which means that we just take the 3-bit pattern and treat it as a 2's complement number. Or it could be biased, in which case we have to take the unsigned interpretation of these 3 bits and afterward add a bias b, which I'll pick negative 3. That's fine. We'll do negative 3. We'll add that to whatever the unsigned 3-bit pattern is, and that will give us our true exponent. So we're going to have to do this across all of these. And I'm organizing this in a way that's very similar to homework assignments that you would see related to this if you are in my course. And the main idea here is that we're going to convert from each of these 8-bit patterns to each of the 4 different meanings it could have had. I better make this barrier larger since it splits 2 completely different examples. All right, so let's start with the simplest stuff, the sign bit. We have a 0 over here, which indicates a positive number. So for all 4 squares, I'm just going to start right off by writing positive. What I'm doing is going to make the top line here be the scientific notation version of each of the interpretations, and then I will go from that to a fractional representation. On this side, for this 8-bit pattern, we know this is negative because the sign bit has a 1 in it. So these 4 are negative. Great. The next thing we want to write is the significand, and that's going to be denormalized or normalized. In a denormalized significand, we take the 4-bit pattern, 0, 1, 0, 0, and we just write it down. And then we insert a radix point after the leftmost bit, or the most significant bit. Now it's hardly most significant from the perspective of being 0, but that is what it is called. So in here and here, there'll be an exponent later, we get the same thing, 0. Well, I'll just write 0.1. We don't really need these extra zeros. I did it the first time so we can see it, and I'll just leave it like this. All right, for the normalized interpretation of the significand, what we're going to do is assume that there is a 1 and a radix that we didn't bother to store, and then we'll copy down the 4-bit pattern. So 0, 1, 0, 0. So that's the 4-bit pattern here. But we didn't really need these extra zeros. They don't tell us anything. So down here, I won't add them. I'll just do the 0, 1, and leave it at that. But there is some exponent we'll have to figure out later. Now let's do the same thing over here. Denormalized, we copy the 4-bit pattern, 1, 0, 0, 1, but we introduce a radix point. This should have been a 1.001, and then some kind of exponent. Same thing here, 1.001, and some exponent. Normalized, we start with a 1 in the radix, and then we put the 4-bit pattern, 1001, 1001, and each of these will have some exponent that we have to decipher. So for the exponents, they are potentially unbiased, in which case we take the 3-bit exponent field and treat it like a signed 2's complement value. So over here, that's 100, so we know it's negative for these two fields. But we have to figure out what the magnitude is. To do that, we'll negate this bit pattern. So flip all the bits, 0, 1, 1, add 1 to that, and we'll get 100. So this is the bit pattern for 4, so this must be exponents of -4. Let's do unbiased for this side. The bit pattern is 1, 1, 0, so we know also that these are negative because the sign bit of those 3 bits is negative. But we have to figure out the magnitude, so we flip all the bits, 0, 0, 1. We add 1 to that, and we'll get 0, 1, 0, or 2. So -2. Now we'll try a biased interpretation of these exponent fields. In a biased interpretation, I read these 3 bits as if it's an unsigned number. So this is the 3-bit version of the number 4. And then I add -3 or subtract 3. So 4 minus 3 is +1. So both of these are +1. Over here, I have 4 plus 2 and no 1s is 6. 6 minus 3 is +3. So in these 2 boxes, we have an exponent of +3. So not so bad. Now all we got to do is start taking it from here down toward a fractional equivalent. So the first thing we're going to do is apply the exponents, and I'll do that all the way across all 8 boxes, and then we'll come back for the final answers. So negative exponents move the radix to the left. Since it's going to the left 4 positions, it'll go first past this 0 and then have 3 more zeros to go past. So that means plus 0.123 zeros, then this 0 and a 1. And I'm not going to bother writing the zeros here because they don't add anything. And so we get so far. Let's do the same thing over here. That's going to give us plus 0.123 zeros, and then a 1, 0, 1, and I'll leave out the remaining zeros. Again, here's negative exponents. So we're going to go to the left twice. So negative 0.01001. And then for this one, it'll be negative 0.011001. We just move the radix point over to the left twice because the exponent is -2. On the bottom, all the way across, we have positive exponents. That's going to move the radix point to the right. In the case of the exponent of +1, it'll move it to the right 1 time. So here, that'll get us 0.0. And here it'll get us positive 10.1. Over here, we'll move it to the right 3 times. So we'll get negative 1, 0, 0, 1, and then the radix point, so 1, 2, 3 times, and nothing in the fractional section. Same thing over here, -1, and then we'll go 1, 2, 3 times just before the last one. 1, 1, 0, 0, 0.1. It was here and went 1, 2, 3 times. So we're almost there. This is the true real values represented by each of these bit patterns in each of the 4 possible interpretations, but I want an accurate fractional version of this, and so what we'll do is convert them just like we did in the video on real binary numbers. So we have no whole part, we know it's positive, and then in the fractional section we have 1, 2, 3, 4, 5 bits. So we know this will be some value out of 2 to the 5th or 32. So as an unsigned value, the fractional portion looks like the number 1. So this is 1/32. Again, because there are 5 bits, 2 to the 5th is 32. 1/32. Now for this one, it's positive, and the fractional part looks like the number 5. But what is it out of? Let's see here. 1, 2, 3, 4, 5, 6 bits. 2 to the 6 is 64. So this is positive 5/64. All right, let's finish the left half up. This one is great. This is positive 1. This one's also interesting. This time we have a whole part. Well, I guess we did here too. We'll have a whole and a fractional part of consequence. So this is the binary for 2. Then the fractional part is 1 out of, well, there's 1 bit, and 2 to the 1st power is 2, so 2 goes in the denominator. This is 2.5. On this side, let's take this value here, and we've got negative, and it looks like a 9 to me. This is 8 plus 1, so it's -9 out of 1, 2, 3, 4, 5 bits. 2 to the 5th power is 32. So this is -9/32. Over here we have a negative, and this is got the 8 and 1 is 9, but then also bit 16 is there. So this is 25. So this is -25 out of 1, 2, 3, 4, 5, 6 bits. 2 to the 6 is 64. So in a unbiased normalized representation, this bit pattern is -25/64. All right, the last two. This here is negative, well, this is 9 with no fractional element. Oh, -9. Over here, we've got negative, let's see, 8 and 4 is 12. And then in the fractional part, we've got a 1 out of 1 bits. So 2 to the 1th power, 2 to the 1st power is 2. So this is -12.5. All right, now that's how we convert from a particular bit pattern to each of its 4 possible representations with the 2 versions of exponents and the 2 versions of significance. What we want to do next is figure out how to take a particular signed decimal real value and then represent it in the constraints of our given floating point representation. So, I'll pull this aside, straighten my paper in the overhead camera, and let's start with, what's a good one? Do negative, I guess. -4.6. So we want -4.6, and we want to convert this to our floating point representation, which I will remind you has 1 bit for sign, 4 bits for the significand, and 3 bits for the exponent. All right. Now, first of all, we know that finding the sign is going to be easy. That's just a bit, right? And since this is a negative value, that'll be a 1. Then we have to interpret the significand, which is a little more interesting because we have to figure out what this thing is as a binary bit pattern. It already is just in decimal. So we know what 4 is, and we'll need to to contain that. So 4 is 1, 0, 0. But we need to know what the fractional part is. So 0.6 is what? Well, it's definitely whatever 6 divided by 10 is, or 6/10, because that's what this represents. So what we're going to do is take 6 and divide it by 10. So 10 is 8 plus 2. And then we'll divide 6, which is 110, by that. Now we know 6 is smaller than 10, so we're going to get a 0 here. But that's because we want the real portion. And whatever bits we get here in the quotient will just get tacked on to these bits to give us the full version of what 4.6 is. All right. So we're going to need some zeros out here. We'll go so far, only go so far out, because at some point getting extra bits isn't going to give us any value, because we're going to have to stuff the whole number part and the fractional number part into only 4 bits. So we'll see what we get here. So 1, 1, 0 versus 1, 0, 1, 0. That's 4 bits versus 4 bits. So we better check the size, or check for which one is bigger. High bits are the same, next bits are different. This one has a 1, so it's bigger. That means we get a 1 here. Now, instead of doing subtraction, I'll remind you the way we do subtraction inside computers is through the addition of a 2's complement value. So we're going to take this bit pattern, flip all the bits, 0, 1, 0, 1, add 1 to that, and we'll get 0, 1, 1, 0. And so instead of subtracting the divisor, we will add its 2's complement with the same number of bits as the original divisor, the same number of bits from the significant one. So that's adding 0, 1, 1, 0. This will give us 0, 1, 0, carry the 1, 0, and then we're going to stop at 4 bits and not continue here. All right, now we got 1, 0, bring down the next 0. And now it's 3 bits versus 4, so this is too small. Bring down another 0. 4 to 4, which is bigger. High bits are the same, next bits are the same, next bits are different, but this has a 0, so this number is smaller. This will have to be a 0, which means we'll bring down an additional 0. And now that we're looking at 5 bits divided by 4 bits, we know this is going to be a 1. So then we'll add our 4-bit 2's complement value, 0, 1, 1, 0. And from it we will get 0, 1, 1, 0. But we won't add anything further than that, because our divisor is only 4 bits. Bring down the next 0, and now I have 1, 1, 0, 0. Actually, that's the bit pattern we started with, 1, 1, 0, 0. So we can sort of expect certain behavior here, a repeating non-terminating value. We have high order bits the same, next bit's different, and this is a 1, so it's bigger. The dividend is bigger, so we're going to get a 1 up there. But this is plenty of bits, because it means that 4.6 negative is really negative 4 point, and then 6/10 is 1, 0, 0, 1, 1, plus some additional stuff. And we can see that there's a repeating pattern, but I'm not going to get into that here because we can't store the repeating pattern. So we now need to take this value and reinterpret it as some form of scientific notation. So we get 1 bit in the significant position of our significand, and this is really the same then as negative 1.0010011, but with some kind of an exponent. So we need an exponent that takes the radix from here to there. So it needs to go over 1, 2 positions to the right. So e plus 2. All right, now just as we did before, that means we need to put this in terms of, let's see, unbiased exponents. A biased exponent, what did we use before? -3. We'll do that. Bias of -3, and we need to do that for d normal significance and normalized significance. All right. So let's see what we get. The first thing we can do is address the simplest issue, and that's that the sign is negative. So each of these is going to have a 1 in the sign bit. 1, 1, 1, 1. All right, then we need the significand, but it can only be a 4-bit significand. In denormal, we assume that the 4-bit pattern will just have a radix point added after the highest of its bits. So since this is our pattern, we're going to only focus on those 4 bits. 1.001, and that's for the denormalized, right? So that means we're going to have 1, 0, 0, 1 as those 4 bits. 1, 0, 0, 1. For a normalized interpretation of the significand, we would actually assume there's going to be a 1 and then a radix point anyway, and so then we want to store the next 4 bits. So for the normalized form, we actually care about those 4 bits. 1, 2, 3, 4, yeah. 0, 0, 1, 0. So we'll store those in the next 4 bits. Only 3 bits left for each, and that's the exponent field. So the exponent in all of these is going to have to be positive 2 in the end. So to get positive 2 in an unbiased 3-bit representation, we just need the signed version of a positive 2 in 3 bits, and that's 0, 1, 0. So for both of these in the top row, 0, 1, 0. So even though I've added a little white space, that is the binary equivalent. And I'll underline it here in red so we can distinguish it from any further work we do. For the bottom row, I'm going to take whatever is in this 3 bits as an unsigned value, and I'm going to subtract 3 from it, and that needs to get me negative 2. All right, so to make sure we're totally clear on this, the true exponent, e, in our case, needs to be, I think I said negative 2 a moment ago, needs to be positive 2. But it's going to come from taking the exponent bits and adding to it the bias, b. All right, so we know our true exponent is 2, and we know our bias is negative 3, so we just need to figure out what the exponent is. So effectively, what do we subtract 3 from to get 2? Why, that's positive 5. But I got to store positive 5 in 3 bits. So that is a 1, 0, 1 for both of these. And I'll just, again, highlight these in color so we can see. That's the binary version of negative 4.6 given this representation in each of its 4 different forms. Now, we could say we're done, but we need to realize that whenever we actually go from the human understanding of a real value and we stick that thing into a computer by converting it to binary, and particularly taking it into a floating point representation, we may not actually be storing the value we want, or rather, the value, once it's stored, would never be interpreted as the value we originally intended. At least that can happen quite frequently, or I should say, infinitely. Now, so what we're going to do next is we're going to take each of these values here that we just came up with, those bit patterns, and do like we did on the previous worksheet, and reinterpret them for what they mean to see whether or not we got an accurate piece of storage. So, let's take this one. We know that it's negative. Great, we know that for all of them. We know that this is a denormalized significand, so that means we've got 1.001, and then we know that we're going to take that to the exponent of positive 2. The exponent is definitely positive 2 for all of these. Let's do the same thing for each of these. We'll do this one here. Again, we know this is negative, and then the significand being denormalized will be 1.001. And because this is a biased exponent, we're going to read this as 5 minus 3. That gives us 2. So e plus 2. Up here, we've got a negative value and a normalized significance, so it's 1 point, these 4 bits, and an exponent, again, of positive 2, because this is positive 2. Down here, we get negative 1.0010 e, and then we have positive 5 minus 3 for our bias, and that gives us positive 2. All right, so then we can apply each of those. Now we have positive 2 exponents. This is negative 100.1. This is negative 100.1. Down here we've got negative 100.1, and over here we also have negative 100.1. I want to note that this is just an anomaly from this random number we picked, and they do not always end up being interpreted as the same thing. In fact, I'm a little surprised. Why did this turn out to be the same with the normalization? Oh, it's because our extra bit only really gave us an extra 0, so it didn't add anything. Okay, I'm totally comfortable with this. So the end result is, this is a negative 4 1/2 for all of these. And hopefully it goes without saying that 1/2 and 0.6 or 0.6 are not the same thing. So the value we stored is not actually a precise representation of negative 4.6. It is close though. It's negative 4.5 effectively. Close. It's off by an entire tenth. I guess that's pretty bad, really. Let's do another one of these. And then we'll call it quits for these examples. All right, the last one was negative, so this one let's do positive. This time we'll go 4.6 is a decent magnitude for 8 bits. So let's go for a smaller number, something close to 0, like I don't know, 14 hundredths. That sounds good. 0.14, 0.14. All right, so we want to convert this to floating point, and I will remind us that we have a sign bit. That's 1 bit, a 4-bit significand, and an exponent that is 3 bits big. Now we know that the whole numbered part is the bit pattern 0. And the 0.14, the 0.14 is what we got to figure out. But effectively, that's the same thing as 14 divided by 100, because this is 14 hundredths. So we can take 14 and divide it by 100, and then we should know what that bit pattern is. So let's see here. 100 is 64, plus 32 is 96. So we need 4 more. So that was the 32. So no 16, no 8, 4, no 2, and no 1. So there is 100 in binary. I'm going to divide that into 14. 14 is 8, plus 4 is 12, plus 2 is 14, and no 1s. And then we know it's not big enough. So we know we'll get a 0 there, and we'll just throw some extra zeros here so we get the final value. All right. Let's see here. Now, when we go to do our subtraction, as the human would do, we're really going to do an add of the 2's complement of this. So the 2's complement negation of this is 0, 0, 1, 1, 0, 1, 1. That's the flipping of all bits. Then we'll add 1 to that. That'll get us 0, carry the 1, 0, carry the 1, 1, and then 1, 1, 0, 0. Interesting. This one and our previous one were both palindromes with zeros on the outside and 1s on the inside. What a coincidence. So let's see here. We're going to go with a 1, 2, 3, 4, 5, 6, 7-bit number. So we need to go 7 bits out at least. 1, 2, 3, 4, 5, 6, 7. The third 0 past the radix, meaning these other guys have to be 0. To figure out if this is a 0 or 1, we got to figure out if this is bigger than this. So high bits are the same, next bits are the same, next bits are different. This has a 1, so this is bigger. The dividend's bigger, then it goes in ones. All right. So we'll add this 0, 0, 1, 1, 1, 0, 0. And that'll get us 0, 0, 1, 1, 0, carry the 1, 0, carry the 1, 0. And we'll forget about the carry after this because we already have 7 bits, same as our divisor. Bring down a 0, and really from the first 1, or the highest order 1 we only have a 1, 2, 3, 4, 5-digit number. So this is going to be 0. We'll bring down the next 0, but we only have a 6-digit number here, so that's got to be 0 too. Ooh, we need more zeros. Here's our 7th 0, our 7th bit, I should say. 1, 2, 3, 4, 5, 6, 7. So we got to compare now. Same, 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 different, and this one has a 0, so it's too small, which means we got to get another 0 down here. We got an 8-bit divided by a 7-bit value, and that'll put a 1 here for sure. And, well, I don't actually even have to add this thing down here because I know I can only store 4 bits in the significant, and from the most significant one, I only have 5 bits worth of data, so I'm only going to be able to store this bit, this bit, this bit, and this bit. That's if I have a denormalized significant. If I use a normalized significant, and we assume that there's a 1 and then a radix point, and so then I can store 4 more bits, but that'll be this, 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 and this. So any further bits we find are totally worthless to us for storage in this representation. So now we can say that positive 0.14 is the same thing as a positive version of, let's see, get this in scientific notation, 1.0001 with some exponent that takes us from this to this. So we need to go from here to the left 1, 2, 3 times. So that means our exponent is negative, for left, 3. All right, now we just need our fancy table that holds denormalized significance, normalized significance, unbiased exponents, and biased exponents, and it was -3 that we used before, so I'll use -3 again here. And we're just going to fill in this table and be done with it. So this is a positive value down here that we're trying to get in. And so all of these are going to have a sign bit of 0. Easy. Now we need the significant. In denormalized, we just take the most significant 4 bits. So 1, 0, 0, 0. And store those. In a normalized one, we assume there's a 1, so we can store, we don't have to store the 1 in the radix, we just store the first 4 bits after that. So 0, 0, 0, 1. Like so. All right, now we need the exponent, which needs to be -3. In unbiased, we need to store a 3-bit version of -3. Well, 3 is 0, 1, 1, so the negative of that will be flip all the bits, 1, 0, 0, add 1 to that, and then 1, 0, 1. So for the unbiased, to store a -3, our 3 bits will be 1, 0, 1, 1, 0, 1. For the biased version, we need to take and put a value into those 3 bits that's unsigned, such that when you subtract 3, you'll get -3. So what -3 is -3? 0. 0, 0, 0, 0, 0, 0. Very convenient for us. So the answer to our first question of how do we convert this to floating point would be these 4 different things, these 4 different bit patterns. All right. But now, like before, we want to know what this means. So we'll reinterpret each of these. This one is a positive, denormalized is 1.0 with an exponent of -3. And we know this is -3 because we just figured that out. For this one, we have a positive normalized, so that's 1.0001 e -3. Down here, we have a positive, and this is what? 1 denormalized, so we just put the 4 bits with a radix point, 1.000 e to the, well, 0 minus 3 is -3, so e -3. And then over here, we have positive, and this is normalized, so we start with a 1 dot, and then put these 4 bits, 0001 e -3. Okay, so if we take this one and move it 3 to the left, we should get 2 zeros and then this 1, and that would be it. For this one, we go 3 to the left, we get 001, 0001. For this one, we'll get 001, and then we don't need to continue. And for this one, we're going to get 0, 001, 0001. Okay, so we're very close now. What's the fractional value contained in each of these? Let's see. So this is a positive 1 out of 1, 2, 3 bits. 2 to the third is 8th. So this is positive 1/8. On this side, we've got a positive, and let's see, 10001. This is a 16 plus a 1 is 17. So it's positive 17 out of something. How many bits? 1, 2, 3, 4, 5, 6, 7. 2 to the 7th is 128. So this is positive 17 1/28. All right, now it has a much higher denominator, so we're going to hope that this one is more accurate than this one. Let's see, down here, it's positive 1, 1, 2, 3 bits, so 2 to the third is 8. Positive 1/8, just like up here. On this side, looks like it's going to be the same. That's the same bit pattern, so this is also positive 17 1/28. Now, of course, the question should arise, well, is that close to 0.14 or not? Well, 1/8 is the same thing, positive 1/8 is the same thing as 0.125. So it is closer this time than we were in our totally previous example, right, where we were off by an entire 10th. Now we're off by 2-ish hundredths, right, or 1.5 hundredths, or 15 thousandths, or something like this, however you like to think of it. So that's significantly closer than being off by a full 10th. On this side, 17 128ths is really the same thing as 0.1328. Yes. So this one is definitely even closer to 0.14. So we have some pretty nice results. So in this video, we reviewed all of the parts of floating point representations at large, really. And we did it with 2 types of examples. One where we start with a bit pattern and figure out what it means in the human world, and another where we take those real value decimals that we have and push them into a floating point representation. Then we reinterpreted the stored floating point representation to its human interpretation and found that at least in none of the 4 different varieties for the 2 signed decimal values we started with, none of them actually stored and came back the same. So that means there are issues with using floating point. And we're going to discuss the primary issues of floating point in a completely separate video. So if you've got questions, please comment below or email me if you are a part of the class.